Yeah, why don't we finish up these last couple homework problems? 231, I think. Okay. So on these things, what you want to do here, I think we went over this a little bit last time, is you want to find the initial strain. So 450 positive, that's epsilon x, epsilon y is negative 90, and gamma xy is 510 positive. Yeah, we went over that a little bit last time, I think. So now there are the initial strains on 231. Now the deal with this, so and you can tell that from the sketch. The original element there is solid, it's a square, and then what's happening to it is a dashed line. So it's lengthening in the x, so epsilon x is plus 450, shortening in the y, so y is negative 90. And then that lower left-hand angle is getting smaller, which is positive shear strain. Okay. So that's where that comes from. Now, we have an angle shown there, so the angle is 73 right there. Now, the strain angles are measured with the horizontal there, so that's 73. So what's going on with that sign convention? You remember the stress sign conventions and the strain sign conventions, or the reference planes are different, right? For stress, if you want to find sigma x1, what you do is you start on this plane, and then you would go 73. Let's just say we're going to find the stress on that plane. This would be sigma x1 for 73 degrees. It would be normal to the plane that makes a 73-degree angle with the vertical, okay? So that's how you would define the stress there, sigma x1 for 73. Epsilon x1, 73, is the lengthening of this line, getting a little bit longer. So, and that comes from the horizontal. All right, so the reason for this difference in the reference planes is so that sigma x1 is the primary causer of epsilon x1, because the normal stress is normal to the plane. So on account of that, they had to throw a little 90-degree difference in the origin of the angle, the reference plane for the angle. So if you come from the vertical, measure to this plane, and then call out the stress that's normal to it, which is sigma x1, that stress will most directly cause the strain, the normal strain at 73 degrees. Okay? So that's why they use different reference planes. You do want to remember this one for stress, it is from the vertical, and then also the one from the strain is horizontal. Okay. So what you would do with this then, looks like I got one ahead of myself there. Okay, you just plug the angles in. I mean, that's really about it. So 73 degrees will get you the normal strain at 73 degrees. You just plug that in plus the values up above, and you get 99. Now, I don't carry that 10 to the minus 6 through. I just do it at the end. Okay, so what that's going to do, that's going to have a strain in that x1 direction of 99 times 10 to the minus 6. And what is that? 0.0000099, is that right? 1, 2, 3, 4, 5. Yeah, I think that's right. So it's not much, you know, just a little bit of lengthening in the x1 direction. Okay. So yeah, it's kind of like the stress stuff. The challenges, the things to kind of keep in mind are the initial values you get, epsilon x, epsilon y, gamma xy, and the angle. And then you just plug it into the equation, all right? And so you'll get 99 times 10 to the minus 6. Now we're looking for this element here, so we can find what we call epsilon y1 on that element too, which would be for 90 degrees more than 73. So you could run that equation a second time for 163 degrees is what you could do, and that would get you the strain at that angle. So you can just run the whole equation a second time for 73 degrees. And you'll get 261 times 10 to the minus 6. Now, there's also a shortcut formula, just like there is for stress and biaxial. There's one for strain. Same deal. So you could get that answer quicker by using this formula down here. You could do it either way. all right? So that'll get you the normal strains on that element, one at 73 degrees and the other 90 degrees off of that at 163. All right. And then the last thing to do here is to find the shear strain at that angle. So again, there's just a basic formula for that. I think it's formula 72 if I remember right. And you just plug into that thing and you just plug the stuff in. So epsilon x, epsilon y, gamma xy. And that'll get you the shear strain, and it's negative 725. Okay. So now you've got the values. Now we're doing a third kind of sketching here. We started off with a rectangular sketch where we used the lower left-hand corner as a reference point. We did that on the homework you handed in here last time. Then we did a circle yesterday, and now this one's more of a schematic. Okay. So the rectangular one we did had the lower left-hand corner as our reference point. The circle at the center is its reference point. This one actually has a little bit more going on. It has a reference point, which would be the lower left-hand corner, and it also has a reference line, okay? So this is more of a schematic sketch that you can dimension. So epsilon x1 extends this corner out 99 times 10 to the minus 6. Epsilon y1 would take that corner and extend it out to 61 times 10 to the minus 6. And then the shear strain at that angle is negative, so that original right angle gets bigger, and we show all that deformation happening on one side so we can dimension it, okay? So that's what the sketch would look like. Okay. So this is probably the least realistic of the three ways of sketching things. It's not really to scale. You just kind of stretch stuff out so you can put dimensions in there. And then you put all of the angle on one side. That way you can dimension it. That's what's up with that, okay? So we're right with that. So that's kind of a representation of what would happen if you took a square and drew it in at a 73 degree orientation and put it on that plate and then applied those strains to the plate. This is kind of what that square would look like. Not quite, because it's kind of a, like I say, it's more of a schematic kind of thing. All right. So that's biaxial strain. Okay, 234 is kind of a bit of a run through this. So there's kind of steps that you do, and you just want to kind of get the steps figured out. And the equations generally aren't the challenge. The challenge is just putting it together. So to put this together, you've got the stresses given. So you know you're going to apply these stresses to that plate. And you want to figure out how much longer that line AB will get. So the steps are, you got the stresses, you use Hooke's law to get to the strains. Then you use the biaxial strain equations to find the strain at 28 degrees. And then knowing the strain at 28 degrees, you can find the new length by taking the old length times 1 plus the strain. Okay. So to me, that's the biggest part of this to get to, understand that. Okay. So we're going stress and material properties to strain in the x and y directions, strain in the x and y directions to the strain at a given angle, and then once you've got that strain, you can find that new length. That original length is 3 centimeters. So we're going to see what happens to it after this stuff's applied. So Hooke's law allows us to figure out, if we know what the stresses are, what the strains would be. And then from there you can use the biaxial strain equations to get the strain at the angle, and then just figure out the lengthening or shortening of that 3 centimeter line. So lots of number crunching here, but that's the overall process to it right there, okay? So, you just do the Hooke's law thing. So that's on the front of your formula sheet on the right, 1 over E sigma x minus nu sigma y. That'll get you the epsilon x, which is negative 0.007833. So it's shortening up in the x direction, as you would expect, because you got quite a compressive stress over there in the x direction. Okay. You also use the Poisson's thing to account for the effects of that one too. All right, and then you'll do the same thing for y. and that'll just be 1 over E sigma y minus nu sigma x. It's just a mirror image of that equation that you see there for epsilon y. And you do the same thing a second time, you'll come up with the strain in the y. Okay. All right, so then you do the bit with the y, and you'll come up with 0.0035. Okay, so that's the strain in the y, that's positive. Okay, and then you also want the shear strain in the y direction. And that'll be what? The stress over G, okay, over the modulus. And that'll get you the shear strain in the xy direction. So that's gamma is tau xy over G, and that'll get you negative 0.004. All right, so once you got that, you just plug into the epsilon x1 equation. That tells you the strain of a line at a given angle. In this case, it'll be 28 degrees. Just plug all that stuff in, run the numbers, and you'll get the strain on that line. It's negative 0.00699. So it's about 0.7% shorter is what's going to happen. That's what's happening with that line. And then once you got that, you just apply that to the 3 centimeters, and you can come in with the final length of that 3 centimeter line. It won't be 3 centimeters anymore. It'll get a bit shorter. Okay. So that's the process on that. So the last little bit on this is right there. You'll get to 2.98 basically. 2.979 centimeters. So it gets just a little bit shorter. Okay. All right, so that's the deal with that. So some of the stuff we're doing, again, it's just a matter of figuring out how to connect the pieces together to start here and get there. That's really what you want to focus on. All right. All right, so that's a little bit there on the strain stuff. Now, the next thing we want to be looking at here is torsion, okay? So what we're starting to look at here are different design situations you might find yourself in. The first one we looked at was pressure vessels, which, I think from a going to work perspective, maybe you'd run into some pressure vessels. My guess is that's a pretty specialized field that you don't design one so much as order one. And there's probably companies that make them, would be my guess. But this next one is something you very well could be working with, and that's torsion. Okay? Torsion is the twist about the center of a shaft. So when I think of torsion, I think of a crankshaft on an engine. I think of a PTO, they call it power takeoff shaft on farm equipment or construction equipment. Any shaft that's spinning there is going to generate torsion. So the torsion is the moment about the center of a shaft, about the long axis of the shaft. Normally these shafts are round, but I've seen some that are kind of square tube and things like that too. All right. So a very good example there would be if you have a motor and then you have a shaft coming out of a motor because a motor twists the shaft, and then the motor would go into a pump, and the shaft then would spin the impeller, which pushes water out of the pump. Okay. So that's a good example there of torsion. Now, torsion has a right-hand rule to it. It's really just a moment, but it's about the center of a shaft. So right-hand rule there, that's positive because that makes my thumb come in the positive direction. When I spin counterclockwise when I'm looking at the shaft, if I spin clockwise looking at the shaft, it'll be a negative torsion. Now, what torsion is, when I think about this and what it does to a shaft, I think of taking a bunch of coins or something and gluing them together, okay? So think you got a stack of coins and you use an elastic kind of rubber cement to glue them together. And then you apply a torsion here, as I'm showing there. Let's say we drew a line horizontally along that stack of coins. If you apply a torsion to that, what's going to happen is each coin is going to twist just a little bit with respect to the previous one on account of having that rubber cement gluing them together. All right, so each one of those lines on the coins is going to move up a little bit there. So that's kind of what I think about when I apply torsion to a shaft. I get a deformation because anytime, you know, in this class, any time we're dealing with materials, if you apply a stress, you get a strain. That always happens. Okay, so what's going to happen there is each coin's going to twist a little bit, and that originally horizontal line will now be an angled line. Okay, so that's what's going to happen there. And also I'm getting shear stresses because twisting is causes a sliding type action. So each coin is going to twist just a little bit with the one before it, and so you get shears building up. So pressure vessels are all about normal stress. Torsion's all about shear. Okay. So if you kind of look at a shaft cross section, cut through the shaft, what you're going to see there is if you have a bunch of little elements, you know, some DA elements that I'm showing there on the top, they're all going to have shears on them. So if you take the shear stress times the area, you get a force. So tau dA is a force. And then if you multiply that force by the distance that little dA is from the center of the shaft, that'll get you the torsion, okay? So there's the fundamental relationship there between the shear and the torsion. The torsion is tau dA, which is a force times the offset distance from the center of the shaft. So if you take all those dAs and add them up with an integral, you'll get the total torsion. Right? And that's related to that shear that builds up in there. Okay? So that's the fundamental relationship that I think about when I'm thinking about shears. Okay? Now R is, I think of R as being rho max. R is the outer radius of a shaft. Okay? Rho is any distance from the center of a shaft to another point. So rho max is R, is how I should have said that. I might have said that backwards, but rho is that Greek looking P kind of letter, okay? So rho max is the outer radius of the shaft. So when you apply these torsions, what happens is that original line from A to B rotates up to A to B prime, okay? And so you have a couple different angles in here. As B rotates up to B prime, I would consider that angle in there to be the twist angle in the shaft, all right? And then that's also going to relate to this other angle. So we got a couple angles going on here. We got one on the cross section that I'm calling phi. It's commonly called the angle of twist in the shaft. And we've got this other angle going on here, which turns out to be a shear strain, is what it turns out to be. Right, because what we can do, we can take the outer layer of that shaft. We could also take an inner layer from E to E prime or an outer layer from B to B prime, like a piece of paper on the outside of a shaft, and just lay it flat on the table and kind of look at it and analyze it. And you might see that shear relationship a little better then. Okay, so if you do that, you'll have two right triangles. Notice they both come from the same twist angle in there. One's has that vertical leg from E to E prime, the other one has a vertical leg from B to B prime. Okay? So they're similar, well, I don't want to say they're similar triangles, they're not, but they're derived from in similar ways. It's just that B to B prime is taken from further out on the very edge of the shaft. So the length of that vertical leg will be rho, be the radius of the rho, whichever one you're looking at, times that twist angle in radians. Okay? That'll get you an arc length around the edge of a circle. So that's this leg from B to B prime or from E to E prime. They both have the same length, which is the length of the shaft. Now if you take a little bit of a square there and rotate it up, it'll turn into a rhombus. Okay? And that will get you that idea of shear strain. So if I take that little square and I rotate the shaft, I apply a torsion to it, see, it turns into something that isn't a square anymore. It turns into a rhombus. And that indicates shear strain going on there. You think of that classic sketches we're making of shear elements. They're I don't know if they're rhombuses, are they rhombi? I don't really know what they are, but they're a couple of rhombuses. I don't know what they are. The plural of rhombus, whatever that is. My Latin was never too good because I never took it. Anyway, so that's shear strain. Well, I can't leave you with a much more profound statement than that, so I guess we'll call it for the weekend here. We'll pick it up on Monday. All right.